Greetings, everyone. All right, so area between two polar curves. This was the last part that we couldn't finish before the end of that period, and so by request, you guys wanted a video. I also posted the notes on Edmodo that correspond to this, that give you all the details, so you don't actually have to watch the video if you understand and can read the notes well, because they're going to say essentially the same thing. So let's go take a look here. So we have our polar axis in black here across the bottom, and we have two polar curves, f of theta and g of theta. And suppose we are interested in finding the area bounded between the two curves on, between some angle or some ray r equals alpha. Okay, so this one here is going to be our alpha, and then some other ray, let's say right over here like this, and this is going to be beta. And so essentially what we're trying to find is, we're trying to find the area bounded between the curves. We're trying to find the area of all this stuff right through here. Now if we proceed with the development development of this, like the development we did of just the area bounded by one curve, we would start by drawing in a couple radial lines going over here, and then we would use the sector, or a sector here, to figure out the approximate the area bounded in that little region, and so on and so forth, like we said in class. But here, if you look at the difference, the key thing to this, in trying to work this thing out, is that I don't want the area of the entire sector. I only want the area of this portion of the sector over here. And so what I'm going to need to do in order to find the area of that portion of the sector is I'm going to have to take the area of the entire little sector here that would approximate the whole region, as if we wanted the whole region, and subtract from it this region over here. And if you look at what's going on here, that should be pretty intuitive on how we calculate that, because the area of the whole entire sector, actually let me go down a little bit so we can still see it. But as we said yesterday, the area of the whole entire sector piece here is going to be given by 1/2 r squared delta theta. I didn't put delta theta in the picture, but that's still that little arc measure that we have right over here. This is going to, let me redraw that. This is going to be our delta theta right over here, like we said in the notes. And so in this case, or for this particular feature, r is given by f of theta, because we're going all the way from the radial, or from the pole along the radial line to the farthest edge, which is bounded by f. And so this would be 1/2 f of theta squared delta theta. And then if we, want to subtract from it the piece here, the one that I drew this arrow to right over here, we'd calculate the area of that little piece just the same, except let's call this b sub I. It's still an area, but I just need a different letter than a for a moment here. We'd still use our 1/2 r squared delta theta, because the angle is still the same. The amount of rotation from one of those green radial lines to the other green radial line is still rotating delta theta. But the bounding function here is going to be g and not going to be f, so this would be 1/2 g of theta squared delta theta. And then of course I'd add all these up to get the entire area of bounded by f, and then add all these up to get the entire area bounded by g. And then of course, to figure out the area of the shaded region that we want over here, this yellow piece, I would subtract. And so we're just going to jump down to that piece right here, and hopefully what we're going to say is sensible. So the actual area that we want, and we're going to jump right into the integrals here, is going to be the integral from alpha to beta, 1/2 f of theta squared d theta. That's the area of the entire region. But remember, we're removing all the stuff that's inside of g, and so we're going to subtract from that the integral from alpha to beta of 1/2 g of theta squared d theta. And then you could just proceed from there and work out the results. But if we want to do a little bit of manipulation, if we want to get a single integral to represent this, since we're using the same variable theta, we're using the same limits of integration, we can write this as a combined statement here, and we would say it's the integral from alpha to beta, 1/2, and then we'd be squaring, so let me switch my order here like this. So it'd be 1/2 the quantity f of theta squared minus the quantity g of theta squared d theta. Now just pay attention to the order of operations on this. The half, of course, is a constant. If you want to move that out in front of the integral sign, that's perfectly fine. But in the integrand, the variable part of the integrand here, we're going to square the outer function in terms of theta and subtract from it the square of the inner one. So it's outer squared minus inner squared. And that would be it. That's how we could find that. Now, just to contrast this a little bit with the area bounded by, two curves in rectangular form, if this is F and this is G over here, and we were trying to find the area from A to B, like this, like we've done many, many times. Again, this is back in rectangular form. In rectangular form, the area would be the integral from A to B, and we would just subtract f of x minus g of x, and do that with respect to x, and that would be the area bounded between the two curves, top minus bottom. The difference here is, notice, that we have to do its outer squared minus inner squared. Times that half, don't forget that, and the integral and whatnot. So it's similar to what we did in the rectangular coordinate system, finding the area bounded between two curves, with the exception here now, instead of our outer minus inner, it's outer squared minus inner squared. And then we have times a half. Okay? So if that helps you remember, or if it makes a connection, or just reminds you of what we did last year a little bit, that's great. If that wasn't helpful, then just erase that from your brain. Now, in the notes that I put on Edmodo, following the development here that I just gave you, there's an example number 4, and I let the PDF that I put online didn't have some shading in it that it was supposed to have, and I'm just realizing that now. So the picture that's there. Excuse me, it's going to come in my classroom there. But there was the solution should have had shading, as you can see in the picture here, which didn't come out in the PDF for some reason, but that's okay. And what we're trying to do here is we're trying to find the area bounded inside the circle, r equals 3 sine theta, and outside the curve, r equals 2 minus sine theta. And so when you plot these on your calculator, or maybe using Desmos or something like that, this is the region we can see the circle. So we want inside the circle, but we want outside the other curve. So we're leaving out this portion of the curve over here. We don't want that included in our area that we're finding. We're just looking at all this stuff up here and trying to calculate that. Now, to work this out, let me get rid of this arrow here. What we need to do is, of course, we're going to write our integral, just like we talked about way down over here, this integral that's in red. We're going to work this out here, okay? So what we have to do is, it's pretty obvious which f of theta is going to be, at least I think, and what g of theta is going to be, but we'll talk about that briefly. The more important thing that we are going to have to determine, or do a little bit of work to determine, is what are alpha and beta. And so, if you can see that the two curves intersect, and they intersect right over here. I kind of missed that one. And they intersect right over here. And so those are the points that we're trying to figure out. Rather, those are at those points we want theta, so that we know exactly where the curves intersect, and so we know which region we're rotating through in order to produce this area. Or in other words, if I was to draw a straight line from the pole to this point over here like this, and then another straight line from the pole to this point over here like this, as this radial line rotates in this direction over here, it's actually going to sweep out the shaded area that we have. Okay, it's going to create that shaded area between those two curves. So it's the two theta values that we have circled in red here that will be our alpha and beta in the integral that we're going to write. But don't forget your algebra skills here. So what do we need to do? We need to figure out where these two curves intersect. So we need to figure out really is when 3 sine theta, actually that's probably hard to read, that's a little better. We need to figure out when 3 sine theta, the equation given for the circle here, or the expression given for the circle, is equal to the 2 minus sine theta, the other one over there. And then, of course, they're going to intersect potentially infinite number of times. We just want those first 2 times they intersect to correspond to the 2 points that are circled in the picture above. And so if we do a little bit of arithmetic here, if we add sine theta to both sides, we get 4 sine theta is equal to 2, or sine of theta is equal to a half. And then from our special right triangles, we're just looking for the first 2 occurrences of this. We should know that sine of pi over 6 is 1/2. That's our first quadrant angle. And then our second quadrant angle is going to be pi minus pi over 6, or 5 pi over 6. And so those values there give you the points of intersection, or at least, the theta values for the points of intersection of those two curves. And so from here, we just got to go ahead and write our integral. And so the area that we're going to have is going to be, I'm going to move the 1/2 out front, just so I don't have to worry about it in my integrand and whatnot. The integral from pi over 6 to 5 pi over 6. And then we are going to have the outer function, one that's further away from the pole. And so the outer function, I think we mentioned this earlier, or no, I said it was going to be obvious, but I didn't mention which one it was. The outer function is this one here. This one's further away from the pole than the other one, and that one's given by r equals 3 sine theta. So that's the one we're going to use first. Okay, so we're going to have 3 sine theta quantity squared, and then we're going to subtract from that the square of the smaller one, or the inner one, if you will. And of course that's the other curve that's down over here. And so minus 2 minus sine of theta quantity squared, and then we just need to do that with respect to theta. And that's what the answer is going to be. You can actually plug that into the calculator. This one here could be worked out by hand. If you decide to try to work it out by hand, it would be a good idea to. Some of the antiderivatives, like when you get sine squared, you're going to have to do a substitution. You can go look in the front of your textbook to get the substitution that you would need for sine squared to get it back down to not be sine squared anymore, and then be able to work this out. The answer, as given in the notes, is, try to drag this up, is given as 3 root 3. But you should work that out either on the calculator or by hand on your own. I hope that was helpful. If you need more or you need something else, let me know. Go study.